Okay, thank you. I have no, I'm off. Yep.
All right, be prepared. Go.
Hello and welcome to episode 24 of Gardin Labs.
Yes! Live at the lab. I'm so excited. What are we doing today, Commander?
Well, that's a very good question. So today is all about water, which is one of my favorite chemicals in existence. So later in the program, Matt is going to be demoing a water detection system that's going to be able to detect all sorts of solubles in the water.
Yep.
So we're going to figure out how that works and kind of get a feel for that. But first, we're going to talk about water in general because water is such a fascinating chemical. It just has so many weird properties that are really, really important for life on Earth to exist.
Oh my God, I'm so excited. All right, so let me break it down. You're going to give us an overview as water as a, I love the way you said this, as a chemical.
Yes.
Which most people wouldn't even use that sentence. So I love it right out of the gate. Then we're going to hand it off to Matt, who's going to demo our new water monitor, which is going to be set up on our aquaponic system, which if you haven't seen it, it is gorgeous. It's a bunch of discus fish from the Amazon that's also working to feed plants above, so it'll be great to check all of the water parameters. And to your point, it is total dissolved solids or electric conductivity, but we'll also be looking at temperature and pH and things like that. So that'll be really good. And so, yeah, let's get to it.
Let's dive right in. So I have some the structure of water, the chemical
Okay,
structure.
all
So
right.
let's go through some of these. So water is less dense as a solid than a liquid. That's very unusual for any material.
Is it the only one that's like that, or
it is
just
not the
one of
only.
the very few?
It's one of very few.
So usually, if something's a solid, it sinks, and if it's in its liquid form,
Yep.
it floats. Except for water, ice floats on the top of a glass.
Exactly.
Got it.
Exactly. And the reason for that is it's usually the energy content. So higher energy, the atoms and molecules are bouncing around really fast. They need more space because they're just moving and hauling. As they turn to liquid, they slow down a little bit. They take up less room. And then when they hit solid, they slow down even more. And that usually causes it to compress. But ice is different because when ice freezes, it expands. And we'll get into why that is.
Oh, that's so cool.
The second one, now this one's a little bit disingenuous because the structure of water doesn't play a primary role, but it does play a secondary role in how how plants transport water through the xylem.
Okay.
Now,
Yep.
I think we covered this 2 weeks ago. The main driver is evaporation. So evaporation from the upper foliage
Yep,
causes
foliage,
a suction
yeah.
effect, which pulls the water up. So this is not quite related to the structure, but again, we'll get into it a little bit more.
Water is clearly very important for plant health, and the way it moves is very important.
Exactly. The next facet is a high specific heat. Now, a specific heat is how much thermal energy it takes to change the temperature of a substance.
Okay.
And each substance has its own specific heat. Water's is abnormally high. And its high specific heat is actually very important to biological functions of mammals.
Okay, as a science nerd, I love everything you said, but I understood very little. Break it down for me. I'm very into fact number 4. What
Okay.
are we talking about?
So fact number 4, water dissolves so many different substances. So many things become water soluble. Think about salt,
okay. All right.
sugar, hydrochloric acid
Yep.
becomes soluble, ammonia. It is very versatile in that respect, and that's what Matt will be looking at a little bit further. Now, before we get too far in, I do have a fun question, and I don't want anybody to cheat, no looking up online. But think about calories and what a calorie is, because it actually does come into play later tonight.
Okay.
So let's dig in.
What is the question, though, that you want people to be thinking about?
Well, it is, what is a calorie? What is the
what
definition
is
of
a calorie? Okay. I love it. So if you know what a calorie is and you didn't look it up, definitely comment, because Commander is going to bring that in later.
All right. So my clicking doesn't seem to be working.
Oh,
so,
there you go.
There we go. Okay, so here we go. These are the atoms that make up water. There's 1 oxygen and 2 hydrogens. Now, a very quick chemistry overview. An atom is composed of 3 elements. There's the electrons, the protons, and the neutrons.
You're bringing me back. I
I
like
know,
this.
I
I
know.
like this. Yes.
So the nucleus, which is the core, is basically just a jumble of all the protons and neutrons stuck together.
Okay.
And then the electrons orbit that, and they orbit at different distances, which are referred to as shells.
Okay.
So the only shells we're going to be looking at tonight on any of the atoms, there's 3 shells. And each shell can only hold so many electrons. So the first shell can only hold 2. The second
Okay.
shell and the third shell can both hold 8. And
Okay.
an atom always wants its outer shell full. It never wants an empty outer shell.
Okay.
And that's what drives a lot of chemical bonds. Now, we're going to discuss 3 kinds of bonds tonight, but the first one is covalent bonds, which is what is in water. So with a covalent bond, we can see in our little diagram here,
Yeah.
oxygen is missing 2 electrons to have its outer shell full, and hydrogen, they're each missing 1.
Okay.
So covalent bonds, what they do is each atom gives up an electron, and they kind of pool them together, and those 2 electrons become part of the outer shell of both atoms.
Oh, okay. That's what makes water, the water molecule, H2O. That's
Exactly.
how the O grabs the H's.
Exactly.
Got it.
So if we can click twice, actually. Perfect. And one more time. So you can see the electrons go
Yes.
in, and they share those electron pairs, but they share kind of like children share a rope when they're playing tug of war. So we have oxygen, which is gigantic, compared to the hydrogen, which is really tiny.
Yep.
So hydrogen, if you can click, Oh, let's see.
Oh,
Oh, there we go.
yeah.
So oxygen's kind of a bully, kind of overpowers the hydrogen and says, you know what, we're going to share it, but I'm going to share it a little bit more. And what it does is it brings the electrons a little closer to it.
Got it.
Now, electrons have negative charge, protons have positive charge. So when oxygen pulls that in, what it does is it charges the whole molecule. So the oxygen gets a negative charge, and each hydrogen atom gets a positive charge.
Okay.
So let's move on and start looking at how cool water is.
I mean, based on the last diagram, very cool. Love
It is
the
very
faces.
So that polarization causes water to create bonds between the hydrogens and the oxygens.
Okay.
Now, in liquid water, as we mentioned, liquid has a higher energy state.
Yeah.
And higher energy state makes it harder for these bonds to form. Now, that's not to say that they don't form at all. You can see these bonds with surface tension. So when you see a glass of water, if it's not full, you'll see at the edge the water kind of goes up into the glass. And if you overfill
You
it,
get a little bubble.
you get a little
Which
bubble.
I think is called a meniscus, if
It
I'm
is. You
remembering
are
correctly.
absolutely correct.
I don't know where that came from.
But that meniscus is created because of these bonds between the oxygen and the hydrogen. These are called hydrogen bonds because they're very common in in chemistry.
Wow. Okay.
So how does so why does ice expand instead? Well,
Yeah.
what happens is that because of the way the oxygen and the hydrogen is arranged, when these bonds slow down, or when the temperature slows down and these bonds start forming more solidly, they create a
gaps.
hexagon.
Yes.
Exactly. They create a hexagon. I tried to find a good image of this and have ChatGPT make one. I didn't get a great one, but this should give you a pretty good idea of what happens.
And then that's the air bubbles. in
Exactly.
ice. Okay.
And
There's
a good way to
gaps
think about it.
between.
Oh, yep.
Okay.
And a good way to think about it is an actual building, an actual structure. If you think about like a building, it is pretty big. If you demolish that building and bring it down to rubble,
Oh, that's a great way to say it. That's
it's
why,
much smaller
yes.
space.
So really, you told me it was a week or two ago
Yes.
why it's so important, based on just the structure of the Earth or the way the Earth works, that ice floats. And I
Oh,
don't
it is-
remember what you said, but I remember loving that factoid. What was it?
So the problem, the importance of this is that if ice didn't float, if it was more dense, ice would form on the oceans and it would sink to the bottom. And the bottom of the ocean is very, very cold, so it wouldn't warm up again. And more ice would form on the surface, and that would
yeah.
get cold and it would come down. And eventually, the entire oceans would freeze over. And if the oceans are frozen over, what percent of life is in the ocean? It's
Yeah, I think
a huge
70% of the Earth is water. I don't know what
Exactly.
percent of life, but yes, it's a huge portion.
Exactly, and the ocean is extremely important in
Right.
regulating climate and temperatures and things like that.
Yeah.
So
Wow.
a solid frozen Earth would not be
That'd
good for
be it.
life.
Yeah, okay. Wow, it's
So-
amazing how it all works together.
Very fascinating.
Yes.
All right, so I have not been keeping up with my notes, so let me make sure I didn't miss it. Miss.
Well,
anything.
you're doing a great job. You clearly
All right. So
love water as a chemical. I believe it.
all right. So now we're going to get into the chemical properties with plants and the xylem.
Yay!
So we have a little visual of a xylem. There's a lot of information on this slide, but I'm just going to do the high level.
Yeah.
So, as Mandy mentioned a couple weeks ago, water evaporates off the top. That creates a negative pressure, causes more water to come up.
Yep.
Now, what's very interesting is cellulose doesn't appear much in the xylem,
Yep.
but it is what makes up the inner walls. And the only reason that scientists think that it does that is because the inner wall of cellulose has a lot of oxygen-hydrogen bonds.
Oh.
If you look in the bottom right-hand corner here,
Yeah.
you can see the chemical reaction, and you can see all the OH bonds.
Right.
So these stick to water. Now, again, this is not the primary thing that causes water to rise up through plants, but this does play a role, the adhesive nature of making sure that the water can
Yep.
actually get up there.
And so I think it's the two ways water moves up in the xylem, and correct me if I'm wrong, is capillary action.
Yep.
Which is similar to, like, if you put a paper towel in a glass of water, the water will climb up on its own.
Yep, and that's what these bonds do. That's
Okay,
capillary
all right,
action.
so that is what this is. Okay,
Yep.
great. And then transpiration, which is the siphon effect of evaporation on the leaf surface pulling water up, just like when you use a hose to siphon, you get that pressure difference going, and you create a suction effect.
Yep.
So there's the two ways plants move water up into their structures
Yep.
and out their leaves.
Exactly. Now, there's one last property of water that we haven't touched on, and that's the solubility. So we have a couple of examples of how this comes into play. So first molecule, oh, I'm sorry. I missed a slide. The
That's
specific
okay.
heat.
I like
specific
it.
Heat. This is my favorite.
Okay,
aspect.
I said number 4 in the beginning, but I actually meant like tell me more about this. This is, I don't think I fully understand this, and I want to.
Okay, so if you imagine an experiment where you have a pot of water
Okay.
and a pot that is solid aluminum.
Okay.
Now you take a blowtorch and you
Okay.
heat both of them up for about 10 minutes.
Okay.
Would you rather put your hand in the water or on top of the aluminum?
What is the boiling point of aluminum? I don't know. I don't. It's
Well-
a great. I would think I wouldn't want to touch molten hot aluminum, but I don't know which
Well, that's
one.
exactly what it is, because
Yeah.
water has a high specific heat, so it's absorbing more of that heat, but not changing temperature as much. Something like metals.
Interesting. Okay, that does help me understand it. So the ability of water to absorb heat is higher than the ability of aluminum.
Exactly.
So it'll absorb the heat and then disperse it around. Which
Well, it
will
just
make
takes more heat to change the temperature, so it can
Okay.
hold more energy. And the reason for
Interesting.
the reason that water specific heat is so high is because of those hydrogen bonds. They are hard to break, and it takes a lot of thermal energy to do that. So when they start forming those crystalline structures, and they water, it's just
Okay.
they don't usually make it very far before the bonds start breaking. But those bonds are so hard that water will just suck up heat and just remain a pretty consistent temperature.
Interesting. And so does it absorb more heat at a lower temperature than aluminum, or can you not say? Am I not saying
It would
that right?
absorb. Yep. So it would absorb much more heat. So
Yes.
if you subjected them to the same thermal energy,
Yes.
water would be less impacted.
Yes.
Than,
Okay.
so you can
Got
almost
it.
think about it like vehicles. Like water is a giant 16-wheeler, right?
Yes.
You can pump as much gas into that as you want. You're not going to get as far as, say, a Prius.
Right. Okay.
So a Prius
Yep.
would have a low specific heat.
Yes.
Little bit of gas, it goes quite a ways.
Okay.
Um,
That makes sense. That's a good analogy.
Now, there are two ways of measuring specific heat. There's one of the primary method is joules per gram per degree Celsius.
Oh boy.
Yes. Which
Sure.
it sounds scary, but all that means is, okay, joules is how much energy per gram per degree Celsius. So if I wanted to measure the specific heat of water, for example, did that? Oh, my
Oh,
clicky
we
is
might
not
need a
working
click.
anymore.
We might need a helpful click. While they're moving through the slide, remind me again, like why this, how this impacts plants and like the ecosystem.
Okay. Well, actually, we got them back. So,
Okay.
So water, if you take 4.184 joules of thermal energy and pump it into 1 gram of water,
Okay.
that will increase the temperature of that 1 gram of water by 1 degree Celsius.
Okay.
If you take copper, for an example, copper only takes 0.385 joules of energy to affect the same temperature change.
Oh, yes.
So
yes.
let's look at some more.
Which is why when you touch a
Yep.
copper pipe in your house, it's either boiling hot or freezing cold.
Exactly.
Because it's literally just grabbing whatever is moving through it. Okay.
Exactly.
Got it.
So I have the specific heat of various materials here.
Very interesting. You of all the things you added olive oil.
Well, I figured, specific
I'm
heat.
just kidding. Oils. Yeah. No, I get it. I just.
It comes into play with cooking and but I'll get into that a little bit more.
No, I love it. Oh, of course, because of cooking. That's why. Okay.
Exactly,
All right.
yeah.
All right. It wasn't that far fetched.
So I said earlier that there's two methods of determining two units that you can measure specific heat with. So the first was joules per gram per degree Celsius.
And you're right. Look at how much higher water is than anything
Oh, I lost my
else.
clicky again. Can you give me a click?
Yep.
All right, the second unit of measurement. Oh, you've ruined it. That's fine. The second unit of measurement is calorie per gram per degree
Okay.
Celsius. And what's really fun is calorie is a pretty universal measurement for energy. The definition of a calorie is how much heat or how much thermal energy it takes to raise the temperature of 1 gram of water by 1 degree Celsius.
Okay, wow, I didn't
So-
know that.
Exactly. So yeah, a very crazy way to think of it, but calories are based off of the specific heat of water. And just for funsies, here's a list of the caloric conversion for the joules.
Oh my God. So yeah, is this the same? Because I think a lot of people don't realize that this is the same as a food calorie.
It is exactly. It is exactly
So
the
if
same.
you were to have a granite sandwich, you would be ingesting 0.189 calories. Is
Yes.
that true?
Well, no.
Per gram of granite sandwich?
Well, no, because that's how much heat it would take to. So you'd have to measure how much heat it already has to determine the full caloric.
Oh, right. Okay.
Yep.
Yes.
But
I
this
see what
is
you're
how
saying.
many calories. So
Yes.
if you wanted to raise the temperature of a gram of granite with your hands, for example, you would use 0.189 calories of energy doing that.
Okay.
Now, specific heat, the biggest role that it plays in human biology, at least, is it's how we cool ourselves off. Sweat is, I believe, about 90% water. So
Mhm.
when we sweat, what we do is we get water on our skin, and then our body temperature heats that water until it evaporates. So the water is absorbing all the heat from us so that we stay cool. Now, if water specific heat was lower, we would need to sweat a lot more in order to be able to maintain the same body temperature.
Wow, that
Um,
is amazing.
it is fascinating the
And-
way all this
Yes,
interacts.
and on leaf surfaces, leaves use evaporation to also cool off, which is wild because obviously they're very far from mammals, which is just crazy. And they also, if you missed a plant, by increasing the humidity, they'll lose less water, and they'll also be able to maintain more photosynthesis, I believe, which is just wild. Oh my gosh, that's crazy.
Yep. Another little fun tidbit is when substances move through the stages of matter, so going
Yeah.
from gas to liquid to solid, or vice versa.
Yeah.
Oh, yep.
Oh, thank you.
Perfect. So what is this comment here?
Oh God, I love it. Part of the reason that liquids tend to have higher specific heats than solids is because more energy can go into molecular motion in addition to vibrating bonds.
Oh, excellent. I was not aware of that. Keeping
Do
in
you
mind,
want to
I'm not a
break
chemist.
down what O7 is saying? I like that it's not 007, it's just O7. That's really clever. I really like that.
So that is something I think I'd have to research a little bit more.
That's really cool. Molecular
But that
in
is very
addition to
interesting.
vibrating bonds.
Yeah, I
Well,
would
if you
have
want
look
to tell
at
us more, O7, this
Yes,
sounds
'cause,
very on point.
my chemistry is all from 20 years ago, so I did refresh my memory on a lot of these
Well, it's
facets.
also something you love. It's something you're passionate
It-
about. You might
yeah.
not have gone to school for it recently, but
That is true. That is
yes,
true.
yeah. One last thing I was going to say about evaporation. I watched this really cool documentary on kangaroos, and obviously they're in Australia in these really hot, dry parts of the outback, or many of them are, not all of them. And they took these thermal cameras of them because they would see them licking their arms all the time, licking their arms, licking their arms. And so they shot them in the middle of the day, and they're, sitting under any little tree they can find, licking their arms, and like their whole body is red and yellow with the thermal camera, and their arms are purple. And they're licking their arms to increase evaporation by putting water on them to cool them down. It's so cool.
It's so amazing. Yeah, I was going to mention. So when matter moves through the stages, so when matter
Yes.
goes from a solid to a liquid, the temperature will rise as it gets closer and closer to liquid, and then when it actually transitions, the temperature flattens out, and it's actually absorbing all of that thermal energy directly into changing stages of matter.
Wow.
And so when you watch the temperature, like it plateaus when it turns into a liquid, and then it starts going up again, and then when it goes to a gas, it plateaus again.
Oh, interesting.
The fun part is when it goes the other direction, it actually releases heat when it changes.
Okay.
So,
So instead of a plateau, it's an extra dip.
well, it kind of is. Yes, exactly. So it does. The temperature actually goes up a little bit when it changes. So
Wow.
in Florida, when they have the oranges for the orange juice and all of that, if it's getting colder and colder and they're like it's going to freeze, to save the crops, they actually spray them with water because the water will freeze, release some heat on the inside, and because of water's high specific heat, it actually can act as an insulator. So it protects the oranges until the temperatures warm up.
All right, is this the same concept then of like snow caves and whatnot, or is this
Well,
a
snow caves are
different
a little bit
concept?
different because snow
It's
caves.
more the air space between the snow.
Well, it's using snow's insulation properties, so it's the same
Right.
insulation properties. But since the water isn't going from liquid to solid, it's not actually
Oh,
releasing.
that's right. You were talking about a temperature change.
Well,
also.
it's a little bit of both.
Yes.
Of the oranges.
Yep. Okay, that makes sense.
All right. Next slide, please.
Let's see if it can click through.
Yep. So now we're
Fingers
going to look at.
yes.
Oh, we went a little far, but that's okay. So we're looking. Oh.
Yeah,
we're
no,
good.
that's the next one, I think.
It is no, but there's an animation here. So.
Oh.
All right. So we're
Sodium
looking.
chloride it is.
Sodium chloride. So this is basically table salt.
Yeah.
So the way table salt forms.
Wait, can we take a quick pause? I want to try to do something for our audio. If that's cool.
Okay,
Yeah,
we're going to take a quick pause for a
absolutely.
second.
Guys, I'm going to try to run this computer straight into the other phone. Give me one sec. And
Have you been able to hear us okay?
it's
Just not as.
background. Let me just start.
Am I unmuted?
And then we'll put the other mic on.
Okay.
So while Matt figures that out.
Sounds like my mic might be working. Yeah. All right. I'll lean in, Commander.
Perfect.
Is that right on?
For those of you who are new to the show, Commander married Matt and I, so he has been a good friend of ours for a very long time.
Yeah.
Yeah, I'm not that good of a friend. He can put his own mic on. I'm
All
just kidding.
So we look at the sodium chloride. So as individual atoms.
Okay.
Sodium has 4, 6, 10, 11 electrons.
Okay.
So that last outer shell. Oh, I'm muted. This one?
Just once. Yep.
Are we on mute?
Am I good? Can you hear me? Yay! All right. So. Seven electrons in its outer shell, so it's one shy. So they form an ionic bond, and an ionic bond is where one electron goes from one atom to the other. So if you can click it, it'll move that purple electron from the sodium to the chloride. Oh, are we good?
If we are able to do one click on the slide, that would be great.
But anyway, so that purple one will move over to the chlorine side. And what that does is it makes the chlorine atom negative and it makes the sodium atom positive. And so those two will attract to each other. And that's how an ionic bond forms. Now, with ionic bond, or with this particular chemical, when it's exposed to water, what happens is the water swarms both atoms. So water will swarm the sodium ion, which is a positive charge. And the negative charge oxygen will kind of butt into it, and it'll separate the sodium from the chloride. So you have each ion sort of in free state the water. So the chlorine will attract the
chloride.
Chloride.
Yeah, that's okay. Yeah. And I remember doing in college doing a saturation point with salt. You know, where you drop it in, it dissolves. You drop it in, it dissolves. But then eventually you'll drop a single piece of sodium chloride in, and it won't dissolve.
Yep, because
there aren't enough oxygens to disrupt right molecules.
Yeah, because they literally go in there and they break them up, and sodium will go off with its one missing electron as an ion and be surrounded by the oxygens.
Yeah.
The chloride will go off in the other direction and be surrounded by the hydrogen pieces. And it'll have that extra electron.
Yeah.
And what happens is as the water evaporates, those two ions are left alone and they start attracting again. so the salt will recrystallize.
And that's how you get salt, well, salt at the ocean that you can see sometimes, but also salt flats. It's because the water has all evaporated and the salt in old ocean has been left behind.
Exactly.
Very cool.
So the next one we have is ethanol. If you wouldn't mind hitting, I think maybe twice. Yep, right here. All right, so ethanol here is lots of chemicals. Perfect, thank you. I have my cookie again. So it's a bunch of hydrogens, two carbons, and an oxygen.
Okay.
And these are all done through covalent bonds. So they're sharing the pairs of electrons everywhere here.
Yep.
Now, how this gets dissolved in water is through that OH on the end.
Okay.
So that acts as, just like water, the hydrogen bonds. And so water will kind of come in there and stick to it and kind of absorb the ethanol into the water. Now, the last one we have is hydrochloric acid. Oh, I'm sorry. Yeah, there's the OH.
Got it. Yep.
Now,
So does it leave behind just carbon? Just the C?
the ethanol stays formed, but it just gets absorbed and dissolves in the water. So
Right.
it becomes water
Okay.
soluble.
Got it. Yep.
Now, hydrochloric acid, this one is actually a pretty complex process. So in its natural state, hydrochloric acid is a covalent bond between a chloride and a hydrogen. And this satisfies all the electrons and everybody gets a full shell. When it's mixed with water, some funny things happen. Oh, my clicky is not working.
And what is hydrochloric? Like, what do you use hydrochloric acid for?
I have no idea. I know, I think
Yeah.
you guys use it.
Cleaning products and things like that. Yeah, I think it's pretty strong stuff.
All right, so yep, so when it's exposed to water, what happens is the hydrochloric acid, the hydrogen actually transfers its electron to the chloride.
Okay.
Which makes the chloride a full, it makes it an ion, but it satisfies its electron shells. And I still don't have clicky. So if you can click one more, that electron will move over. There we go.
Oh, yeah, I saw a little purple guy make a jump.
Yep. So now we have this hydrogen that has no electrons. So what happens to that is it actually bonds with the oxygen in water with a covalent bond. But instead of having each atom contribute a single electron, oxygen contributes both electrons. So if you click one more time, you'll see the hydrogen from the yep, there we go. So that forms a covalent bond as well. So you get H3.
Wait, pause for a second.
Quick pause, can do.
Pause.
Working on it.
All right.
Right now.
And that's pretty much
Can
everything.
you hear us? Nice.
You can hear? Perfect. Well, with that, I'm wrapping up because this is the last thing I had.
We have some slides on some of the monitoring that we're going to do, and basically just an overview of electroconductivity, parts per ppm, parts per million, total dissolved solids. Oh, here we go. Okay, great. They're up. Well, first of all, check out this awesome slide that Andrew created the entire deck. But I mean, what a great way to hit water monitoring. And if no one is aware, this is a monitor lizard. So although it would be very exciting to be talking about monitor lizards right now, and I think we should bookmark that for a future show. We won't be talking about monitor lizards. We'll be talking about water monitoring. So yeah, let's jump into it. And this is a great, we're going to go through all the parameters, kind of the primary and the secondary. And then we're going to be talking about them in a few minutes as pertain to our beautiful discus aquaponics tank. And we'll use the water monitor that we have. Okay, so let me see. So primary, primary parameters that we're going to look at is, you can see that we've looped together, you can't quite see it, but my commander's body is sitting over the letter T. TDS, EC, and PPM. And TDS stands for total dissolved solids. EC stands for electroconductivity, and stop me if any of this doesn't make sense. And ppm stands for parts per million. All three. Yes. All right.
There we go.
All three are measuring the same thing. Electroconductivity is like the raw measurement of this. It's how much electricity can pass through the water, and why do we care? It's basically saying the more nutrients or salts or food, if you want to think about it that way, especially in a hydroponics or aquaponic system, is in the water, the more electroconductive it is, so the higher electroconductivity. Total, both are actually measuring the amount of dissolved solids in the water, or excuse me, all three are. Total dissolved solids in parts per million are just a conversion on electroconductivity. So all three of them are the exact same measurement. How much nutrients or dissolved solids or salts, however you want to think about it, are in my water. But do you want me to talk about it in a measurement measured as TDS, EC, or ppm? And so oftentimes you might, different nutrient mixes or whatnot, or kind of how-tos might say you want to aim for a parts per million, or you want to aim for a TDS. And they're different numbers because the conversions are different. But at the end of the day, we're all going back to the exact same thing. So that's why they're all listed together. Any question on that? Did I explain that decently?
I think you did, but I just wanted to make sure I understand you correctly.
Yes.
So all three of those measurements,
Yes.
there's not a consistent conversion across. It varies depending on the substance you're measuring, correct?
Say that one more time. I want to make sure I answer correctly.
All right. So, for example, if you're looking at
TDS or whatever. Yeah.
Okay.
Yeah.
So,
Okay.
like, if you want to convert TDS to EC.
Yeah. But everything is this very specific. How well does this liquid conduct electricity, which will tell me how much food is available. And so.
Oh, hold up, we lost audio.
Oh no, I moved. Myself, I moved my little receiver into my pocket because I had it out when I unmuted.
You're good.
Okay. Are we back?
Yep.
Okay.
We're back. All right. So feel free to comment if you have any questions on this. One of the ways that this is always stuck in my head is Matt and I were setting up a really cool, we did our ultimate citrus tent environment, and we set up a flood table with a reservoir, and we pumped a bunch of our fish tank water in there, and we set up on a timer so that it would flood up into the pots that were up above, all of our lemon trees, and then it would drain, and some orange trees as well, and then it would drain down below. And I'll never forget this clarity moment I had on this number. Matt put the meter in, which we're gonna show in a little bit, and our parts per million was what this meter was measuring, was low. And Matt was like, oh, we're out of food. We have to add a really good all-purpose and a salt-based one so it will dissolve right away because these plants don't have enough food. And I remember it was mind blown. And then so we scooped in a bunch of salt-based, all-purpose, a 20-20-20 mix. And then, it ran for about 3 minutes spinning through the system. And it was it went right up. And it's that's how you can tell how much food's in a system. And conversely, you can have too much. You could test that ppm and you are just drowning your plants in nitrogen and they're not gonna make it, especially depending on the types of plants that you're growing and their tolerance for high nitrogen or salt or fertilizer levels. All right, any other questions on that one? It's a tricky one, but it's really important. It's
No, I think you explained it very well.
Okay.
It makes sense to me.
Okay. I wasn't fishing for a compliment, but that felt good. All right, pH. I always, whenever I have someone come to the shop and they say, should I measure my pH? Why does it matter? The way I like to explain pH is pH, and we actually created a little video on this, but imagine that all of your nutrients are like a buffet table, okay? You've got your nitrogen, your phosphorus, your potassium, your calcium, your magnesium. and your plant wants to go ahead and go through that buffet or your soil mixture or your water mixture if you're doing hydroponics or aquaponics, and it wants to grab the nutrients that it needs. It's putting on a ton of leafy growth, so it needs a lot of nitrogen. It's about to pop up a couple flowers, so it needs some phosphorus. Its stems are weak, it needs more calcium. If your pH level isn't in a range at which your plant operates to grab those nutrients, it's like putting a lock on the buffet. So if your soil or water mixture is filled with calcium, let's say, and your pH is off, it doesn't matter how much is in there. That little nutrient table on the buffet got locked down and your plant can't get it. And so people will say to us, I know I put the right ratios of everything in, my ppms are perfect, everything's great. And I'll say, what is your pH? And if it's too acidic or too basic, based on what the plant wants, it doesn't matter what you have in there. It's not able to grab them. And then we're also gonna throw this monitor, obviously, in our discus tank, as I keep mentioning. And pH is also critical for fish. So if you have the wrong pH, it's too acidic or too basic, you can also kill your fish. And different fish and different aquatic species can tolerate different levels of pH. So we have a nano tank, we call it, that's filled with shrimp. And if that pH drifts into acidity, it actually melts those shrimp shells and we'll get die-offs in the population. So they can't handle acidic, whereas other animals can. They can handle a slightly more acidic environment. The other thing that I'll say about pH, which is really interesting, is, anytime you're getting breakdown of organic compounds, plants that are just shedding and dying, fish waste, things like that, they can be adding acidity into your system. So that's another reason you really want to watch out for it in an aquaponics or hydroponic system. Any questions on pH?
No, I think I'm good.
Okay, we are just running through it. Okay, and then temperature. I feel like less known in the plant world, temperature. Obviously critical when it comes to an aquaponic system because of the health of the living animal species in the system. The snails, the fish often need a very specific temperature, and it often can vary between species. We keep our discus tank very warm, into the almost 80 or a little bit above, whereas other tanks you can keep colder. But obviously that's fish. You're like, but lady, you guys are usually talking about plants. What's going on here? Well, with plants, as we all know, use their root systems to pick up oxygen. If your water is too high, there won't be as much oxygen in it, and you could inadvertently create a root rot scenario, and or some plants, just a tropical species versus a cold weather species, can or can't tolerate cold or warm water. In addition, higher temperatures often can introduce more pathogens, which obviously can be tricky. If your water's too cold, it also locks out nutrients because it can prevent the plants from running on their optimal conditions, and that'll prevent photosynthesis and them able to bring the nutrients up, which makes sense. If they're sitting out there in the freezing cold, if you think of an extreme, they're not like actively photosynthesizing and breaking down nutrients and sucking up water, So water temperature can be really important, but for the most part, you just don't want extreme swings. Like I said, we have the discus tank at a really high temperature, and you'll see the plants that are using that water just look gorgeous. They're all tropical varieties and they're totally cool with an 80-degree water. But if we had put like leafy greens in there or cold weather crops, they might not look that good. So something to think about. And somebody wrote cold water holds a lot more oxygen, and you are correct, which is actually a big part of the migration. When you see huge migrations of whales and things like that, they're moving from warm water to colder water to get food, to fatten up for breeding season or whatever it might be. So that's kind of how I think of those three parameters. Any questions?
No, you are nailing it. It makes absolute sense.
All right, okay, let's go to the next slide. I think the next one is secondary, but we might be surprised. Yes, okay, good. All right, yes, Andrew did all these slides. He gets one more shout out for just making it happen, because what a load to not have to worry about putting these together. So thank you again, Andrew. Okay, Secondary things to measure. The way I think about it is, if your plants look great, your fish look great, your pH, your temp, and your total dissolved solids, or ppms, whatever you're measuring, your EC looks great, these are probably also great. But if you have an issue, if you're like, those don't look great, things seem to be not go, or those look good, but things don't look, my primary parameters look good, but things still don't look quite right, you're gonna wanna dig into these, and I'll tell you why. So nitrogen, as we all know, is one of the primary food sources for plants, and especially plants that are in the growth stage before they hit flowering or seeding. And in a system like an aquaponic system that we're going to show you, the fish waste is creating ammonia, the breaking down of organic matter is creating ammonia, and all of these things are toxic. Like, fish and plants want these to be at 0. Like, they are not tolerant of ammonia. And this is gonna blow your mind. Do you know what breaks down ammonia? Do you know how the plants in that aquaponic system access that ammonia?
No idea.
Bacteria! It's you guys, it's amazing. Everything works together. So beneficial bacteria work on the ammonia, and they convert it briefly into nitrite, which also nobody likes. Toxic to plants, toxic to to the fish species. And then it gets converted into nitrate, which plants love. So that's another reason why when you have like a fish tank or even a well-functioning hydroponic system, you don't want to do a complete water change, because you've established these beneficial bacteria, these microbes, everybody working together to turn this stuff into things that the plants and animals can use. And if you drain that thing to 0, you gotta start all over again. And that's when you can get ammonia buildups and whatnot. So if your plants and animals are struggling and your other parameters look good, you might be having a buildup of ammonia or nitrite or even nitrates. So Matt and I had a disease move through. We had a beautiful aquaponics set up going with our passion fruit. And over the weekend, when the shop was closed, a disease moved through the passion fruit and they all started dying. Well, they're not actively taking up the nitrates out of the system anymore because they're dying and they're getting root rot and all this other stuff. So they're just dumping them back into the system, where then the fish started to suffer. So ideally, if you've got everything balanced out, the amount of nitrates that are being produced are able to, is a hero there.
That is pretty amazing. So what is the difference between nitrite and nitrate?
Yeah, it is a brief intermittent stage in the movement of the compound from ammonia to nitrate. So, and I think it's N, we should look it up, but it's like, it's the, it's got an extra, it's got an extra atom on, an extra nitrogen, thank you, I'm like blanking.
Okay.
It's got an extra nitrogen, which then it loses and becomes nitrate. So you almost always, you won't have nitrogen, a nitrite, it's a fleeting molecule in between ammonia and nitrate. Okay, oxygen. Seems pretty simple, but sometimes we forget, like roots have to have oxygen to survive. Obviously the plant is taking in carbon dioxide and water to photosynthesize and create energy, but its roots are uptaking oxygen. So if there is not enough oxygen in the system, or if the water is too warm and it can't hold enough oxygen, then those roots can't pull that oxygen up and you're gonna get a crash. In addition, if you're running an aquaponic system like we are, if there's not enough oxygen in the water, the other species in the tank will also be upset. So obviously things you can do if you don't have enough, it's often measured as dissolved oxygen. So it's how many oxygen molecules are floating around in your water, how many little bubbles are in there, whether you can see them or not. Things you can do is like add air stones, add a little waterfall, or if you're not worried about the species in the tank, you can cool the water down, and just by definition, it'll be able to hold more oxygen. So that's another one. And then my favorite.
Oh, actually, before we go to the last
yes.
one, so I'm curious, are the roots actually pulling in oxygen O2 in the gas form?
I believe so, which
Wow.
is why if you get circling, when a plant is root bound, what is happening when it's in like a constricting space, so let's like a plastic pot, it's hitting the side and that's like, whoop, I can't go anymore, so it turns. The turning that is killing it. It's the overlapping of itself on itself, which is preventing oxygen flow, which is causing root death.
Oh, that's very interesting.
Wild, right? Plants
Yeah,
are amazing.
Very fascinating.
Yeah, it's really cool. Which is that we grow a lot of the times in fabric pots, and actually this will blow your mind too. For those of you who don't know why fabric pots are super cool, fabric pots provide air pruning. So what will happen is the roots will move out, and then instead of bumping into a plastic side, they bump into the fabric, which has air on the other side. They can feel the air. I mean, I don't think "feel" is the right word, but I don't know, maybe it is. They can feel the air. It's impossible for them to circle. Instead, what it does is it triggers a response for them to branch again. Because I think it's because I don't know, maybe, I don't want to say this, they think, but it's as if they've hit the surface, like whoops, so they just branch again, they make more. So in a fabric pot, you actually get maximum amount of root surface area for pot size. Wow. Because it'll bump, it'll branch, they'll bump, it'll branch, they'll bump, it'll branch. So it's like you're just getting all these tiny little root surfaces that are then able to go bring up water, oxygen. And that's the other thing about when you were talking about water that's so interesting, is not only does the plant bring water up, but don't forget, like if you drop a banana peel into your pot, like the plant can't access that. The plant uses water to grab the oxygen and the nutrients up too. Like it's huge. It's why you gotta keep your plants watered. It's how it's maintaining all those functions. It's how it's bringing food in. It's how it's respirating out to cool down. It's just amazing.
Yeah, I mean, it's a fascinating chemical substance.
I love that you call it a chemical, because most people don't. So it really just illustrates your understanding. I love that.
I mean, I like to make a distinction because when you talk about, because you can talk about water in so many different fashions.
Yeah.
When you're talking about it as a chemical, you really should. That's how you have to refer to it.
I love it. No, I think it's awesome. All right, hardness.
Yes.
Any idea of what that is? I don't want me to put you on the spot, but I thought it'd be fun.
It's iron in the water, isn't it?
It's not iron, it's carbonate.
Oh.
And you're gonna love this. This is gonna be very chemistry focused description. It acts as a buffer, okay? Are you familiar with buffers? Do you want to tell people what a buffer is? I'm not trying to put you on the spot, but it is very chemistry driven, so I wasn't sure. Okay, so I'm not trying to put you on the spot, but here you go. I'm gonna do less of that. I'm gonna stop doing that.
No, it's fair, but I have no idea what a buffer is.
All right, so think about it this way. Carbonate, the way to think about it is, it's in charge of stopping the pH from having wild swings, okay? So if I have pure water and I drop one little bit of citric acid in there, I drop in one Sour Patch Kid, that's gonna make it acidic because there's not much else in there.
Yep.
And if I drop in one tablespoon of baking soda, that's gonna make it acidic because it's got a lot, that's gonna make it more alkaline. So what a buffer does is it works as a sponge to stop the wild swings. So once you've set your pH where you want it, or once it's neutral, you can add your buffer in, and then your buffer will say, "Oh, let me grab that Sour Patch Kid. Oop, let me grab that baking soda," and it helps to even keel it. So if you find that when you're doing water changes, you're getting these huge pH swings, it's because all of a sudden your water was really acidic because there was tons of ammonia, nitrites in there. There was a ton of dead organic matter. All these things are adding acid. You're like, oh, I better do a water change. You take it out, you add some water, and all of a sudden it's super alkaline. It's because your carbonate, your hardness of your water, you don't have enough buffer in there to help steady everybody out. It's just going with the changes.
So is the hardness the buffer?
So carbonate is what is the carbonate is the K essentially in the KH definition of hardness, and it acts as a buffer.
So okay, so the hardness is actually good in that sense.
Yes, exactly.
Okay.
And so the hardness of your water, once you measure it, you will want it to be harder or softer depending on your plants and your species. But we add to all of our tanks like oyster shells, or if we find like washed up on the beach like old pieces of coral and stuff, we'll drop them in and they work as natural buffers. And we very rarely have to do pH checks on them because it's just kind of the system is running, and those things in there are helping us run that system.
Okay, that's very interesting, because when it comes to house water, for example,
Yes.
hardness is usually considered bad, and they have water
Right,
softeners and
right.
things like that.
Yes, yes, yeah. Well, and I think there's degrees of hardness. It's actually measured in degrees, and so to your point, you can't have it be too high or too low. But
Yep.
as a general concept, the thing that you're measuring is carbonate, and then you have your degrees of which it exists.
Fair enough.
And you don't want none of it, and you don't want a ton of it. We don't want a full oyster tank aquarium. All right, do we have another slide? Oh, live demo!
Yay!
All right, what we're about to do is gonna be super cool. The camera is all of a sudden gonna change. It's gonna flop over to our live demo. I'm so excited. I'm gonna wait until I get the green light that we're doing it. But while they're getting set, is there anything else that we should cover with these parameters?
There's so much more we could talk about to water, but I think we've covered the big things.
I think it's good. The meter that we're running, that we're about to show you, is a continuous water monitor. So it's designed to sit on the outside of whatever water source you're running, which again, ours is gonna be the discus tag. And it's got LCD screens that perpetually show, because there's probes sitting in the water. Oh, we've switched. Okay, yes. Do you need to switch my mic? Oh, keep talking. Okay. They're getting ready. That adorable gentleman in the dinosaur sweatshirt is our son, Ben. And the other adorable gentleman in the hat is my husband, Matt, and the adorable little lady to the right is our daughter, Lucy. And they came in here to help us tonight, because who doesn't like playing with the fish tanks on a Friday night when you're supposed to be getting ready for bed? I know I do.
Friday night is for partying and fish.
Yes, we also took them to the convenience store and let them pick out whatever candy they wanted. So we're getting A+ parenting all around. It looks like Matt is feeding them bloodworms, if I had to guess, which of course the kids love putting this stuff together. All right, we're gonna throw it over to them. It looks like they're ready. Get ready for the coolest continuous monitor you've ever seen.
Because how it falls down, you want to wait, let them eat, and then you give them a little more. All right. You're live. Yeah. What's going on? Nice job, Lou. All right, Ben, you want to get the last of it? I love that. That's perfect, bud. Little bursts. Nice.
Is that good?
Great. Good job, bud. Great job. Go ahead. Ben. Yeah, thanks, Ben. Great job, Ben. Yeah, okay. Gotcha.
Good job, you guys.
Job, Lou.
This looks great. Ben, do you remember what kind of fish are in there?
Angelfish.
Oh, that's the other. These ones are discus fish, but very close.
Fingers out, Louie.
Very close. I keep stumping people by accident. You know, they look very similar. The angelfish are on the other tank, on the other side of the rub. These
They're
ones are all
related.
discus
They're
fish.
cichlids, and they're from the same part of the world, actually. They're from the Amazon River in South America.
Angelfish are from the Amazon too? Is that what? Wow, I did
Right?
not know that. No, you could totally be right. Oh yeah, no, that wasn't I.
That
was I didn't know. Wow.
I think so.
All right. We
Cool.
came
Thanks,
over
guys.
to set up the continuous water monitor.
Let's do it.
I can take the kids off your hands if you'd like to show everyone.
Sure.
Or I can
Are we
stick
still
around.
live?
Stick around. I got the
All
kids.
right.
Yep.
Okay, you're amazing.
We are.
Bye.
Love you. All right, you guys want to say goodbye to the camera?
Yeah.
Bye.
Viewers.
Like and subscribe.
Thanks, bud.
Thanks,
Yeah.
Ben. Good work, buddy. Yeah.
Bye.
Yeah, all right. Okay,
Like and
so we're gonna
subscribe
cover.
again.
Come on, guys.
Is my sounds all right? You guys are the best.
Give us a...
Yeah, are we good? Oh my God, look at how gorgeous. You know what I think I might do first? Should I just quickly show you guys this system? And community, you want in on this? You can ask some questions if you want. You guys, Matt built this. he loves, you're like, no, we both did it. No, this is 100% Matt. So these are discus fish. We've had them for years. And you can see we've got them in a planted tank. There are some bristlenose plecostomus in here that were actually born here. They were born in another tank. There's one Cory catfish, whose name is actually Commander. We named him years ago. He's like 8 years old. And then we've got a couple snails in here. So the way the system works is we have a redundant filters that we can run just because the shop is closed 2 days a week. And as I mentioned, we had an aquaponic system crash years ago. So we do have a filter that we can use as well, just in case anything ever happened with the plants. But the way it works is the pump that's sitting in the back here, you can see it's got moss on it. It's on a timer, and that timer turns on and it runs up this pipe, boop, 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 and then floods this flood table here. And so then the water moves across the entire flood table. Look at how happy these plants are getting their, fish waste water. Moves across these plants, and then you can see there's a pipe here. It drains out and comes back in. So the roots are acting to pull up that nitrate that the fish don't want, which has been converted from the ammonia that they especially don't want, and nitrate that's in the system, and clean it. And then, of course, the plants are absolutely loving eating that nitrate. So that's kind of the idea behind an aquaponic system. I think the other thing to show is just how we have these. I'm actually going to use this very convenient backwards chair. I just wanted to show, this was another one of Matt's brilliant ideas, what these plants are in. I'm going to see if there's an easy one for me to grab. Actually, this might be perfect. Is it? Well, it's hard to see, but they're in little net pots, and most of the net pots are filled with biochar. Let's see if I can get like a handful. Yeah, here we go. So you can see, so it's a net pot, which if you don't know, let's see if I can at least find a little guy. They look like this. They have these holes. Look at all those roots. So the roots can come out. And then biochar is the primary medium that we have. So essentially the biochar is working as basically just a structure to hold all of the roots. But in addition, biochar is amazing because it holds microorganisms or microbes, moisture, and also excess nutrients. So when the table is sitting in this kind of moist, nutrient-filled ecosystem of biochar, and it has worked very well, as you can see from the plants that are up here. I mean, it's just, they're really letting it. We do have, just to give one more update on the system, above me we do have a row of LED lights, which is also really important for tropical plants. If you don't have it, they just don't look this great because obviously they can't photosynthesize at the rate that they want. So that's definitely a key component as well. So we need to make sure that we've got all of our parameters correct so that everybody stays happy and healthy. And we got this super cool, I'll show you what it looked like. We just got these new monitors in, which you can control from your phone app. And they come in a really cool case. All right, so let me just pull this baby out and get it plugged in. This is a probe, and we'll get this thing set up. And then, like I said, we'll quickly talk about each of the primary things we want to measure, and I'll see if I can convince Matt to join me on screen, and he can talk about how he has dialed in those primary measurements for these discus fish. A lot of times people will say these are one of the most difficult aquarium fishes to keep, but Matt has really found a way to use these planted tanks to just make them about as happy as they get, I think. We've had them for years and years and years, and they're doing just awesome. All right, hold on, let me get everything plugged in. We'll make this happen. Yay, you're joining me. I'm so excited. I know you always say it's both of us, but this aquaponic system is your baby, and I really want you to talk about it.
I put these chairs here. I'll move these because these are just for the...
Well, yes. And then also me when I climbed up there.
Man, yeah, I'm so stuck. It's like, so I had a monitor on here for a long time, and it's funny, I don't see them ever at aquarium stores or talked about. And
I'm just gonna
I
get some
have to say, I had
shears.
one for years, and they're so valuable because you look at them. If you monitor by checking, you're doing it. Let's just say you even do it once a day. If you're that disciplined, no one ever does. No one ever really does. But I have this set up. I'm walking by it 20 times a day, let's say, looking at the different parameters, the pH, the TDS, the ppm. And when you hear TDS or ppm, it's electroconductivity, and it's multiplied by some metric, like some specific number, like 500 or 700 for ppms. But it's all ultimately the same thing. It's measuring basically how much electroconductivity there is, and it's assuming that represents like contaminants in the water. But the truth is, right, if you put 100 parts per million of iron in versus something that wasn't as conductive. Jeff, what's a non-conductive thing that would be soluble in water, bud? Like something less conductive, like iron being highly conductive, a metal. Sodium is probably less than iron, right?
Sodium doesn't seem like it would be conductive. Well,
It is, but not as maybe. So let's just say 100 parts per million of sodium versus 100 parts per million of iron. The meter would actually say like 500 for iron and 100 for sodium, let's say. But what's important about those three metrics is that you see they're stable. And from what I found is if my pH, my ppms, and my temp are all stable, everything else, all the other parameters, the different hardnesses are usually stable. If I see my pH start moving, at the end of the day, it's probably got something to do with my hardness, right? Like maybe there isn't enough carbonate in there or calcium in there that I need to adjust, and that's why the pH was shifting. If I see my ppms all of a sudden start going up, well, I can guess that it's probably like nitrates or ammonia. I have to go look in and I'll start doing specific chemistry tests. I mean, oxygen's something, I guess none of those, well, if your temps start going up, you can assume your oxygen might be going down. So monitoring temps is really important, especially if you have heaters. It can be too high or too low. So I haven't had a meter here in about 2 weeks, and I feel a little blind. The fish have been looking good, and I've been monitoring the temps daily. These guys are particularly sensitive to change, and these guys have really humbled me. And it's funny.
Sorry,
I'm so sorry.
What am I? Oh, here. Never mind. I'm like, how do I wanted to hook this off the side. Sorry,
Yeah, we
I
should
got
get
it.
back
I got
to
it.
this,
I figured it
I'll
out.
stop rambling.
No, You're not
upside
rambling.
down, upside down.
You're not rambling.
Oh,
This
here,
is
go
why
like this.
This is why we're here.
All right, cool.
Keep going. I did not mean to interrupt you. I apologize.
No, you're good.
Yeah, no,
So that slides like this.
You got to get that clip on.
I tend to break stuff. So, well, that's
Cut this open.
one thing that's nice is about having a garden supply store is if I'm using something like this, and if I do break it, I get to know whether, I'll know like, all right, this is too fragile. I've tested lights out where I remember getting one wet and I contacted the manufacturer because I try to treat them rough and he was like, oh, if they get wet, they're ruined. I'm like, well, my customers are going to get them wet, so I'm glad I did them a solid before.
Matt, am I putting both of these on here, or where does this one go?
Yeah, so this is the pH.
Okay.
Typically. And you can use, they're all the same. So
What's
if this
this
guy
one?
broke, let's say, and that is going to be the electroconductivity.
Okay. And this is temp, it looks like?
That's temp. Sometimes the electroconductivity and temp are the same.
Got it.
Let's just pop it in.
All right, so we've got 3 ports. Can I put this one in too?
Yeah. And you don't want to actually
sorry.
put
Sorry,
them
fish.
too close to each other.
Oh.
I forget. I remember, oh man, I wish JT would be able to tell me, but some of them, I forget which one. I think the pH might, oh, whoops, guys, hilarious. I'm like, why is this floating?
Oh, the cap.
The cap's on this.
Yeah, that's what happened.
And so, see, there's like a little salt buildup. I'm actually, before I put this in, so this is a storage solution. I'm actually kind of bummed it's dried out like that because that means the meter is drying out, which isn't great. So I'm going to dip this in something not in there because I don't want that storage solution to get in the tank. Hold this for 1 second.
Got it.
Grab a little cup.
Do you know why you store stuff in storage solutions? Like why you have to do that, Matt?
For sure. So the storage solution, basically the probe, I don't know if it's porous, but
It's this white.
over time, if it's not stored in, you store it in a potassium chloride solution, it keeps it from drying out. And unfortunately, this one looks like the solution had leaked out.
Yeah.
So it's probably a little dried out, and as it dries out, it'll resaturate. And it's funny, I've found like these meters, if you keep them in an aquarium, it's unbelievable. They'll last like 5 years.
Oh, just because they want to be.
They're stable. It's when you
Yes.
have, these meters are like your traditionals, right? Now you can see I keep it in a ton of solution because I don't want it drying out. And again, I'm going to dip this guy in, and that keeps it from drying out. But if it's just sitting continuously in these, they also last a lot longer. So these continuous monitors, like I think this one's $90. And it's great because they last a lot longer. You have continuous read off it. You don't have to ever actually do the meters. You don't have to calibrate as often.
All right, press the temp cal plus key to choose between Celsius and Fahrenheit. Okay, we want Fahrenheit. We got it.
87.8, huh?
Well, then hold it for 5 seconds to calibrate.
Huh. To calibrate temp?
That's what it says. No, it looks like it's calibrating something else.
How's it calibrating temp?
TDS.
Never heard of calibrating
To
temp.
calibrate mode.
Okay, so we might need to get something to calibrate it.
No, it says to put like this, but I mean I don't.
This
I shouldn't
makes
say no. Choose your method. Oh, because how would you calibrate to this? I know what you're saying.
into testing solution.
Oh, that makes sense. You can't calibrate on unknown.
Yeah.
Okay, yeah.
It's
yeah,
cool.
yeah.
All right,
So
so
it's
did it
just like
come with
ca-
some testing solutions?
I don't. This is everything that I saw, but I can get you. Oh, you've got. You want me to get you some cups?
Yeah,
Okay.
let's see. Oh, there's an app for this guy.
Yes, it's
Lot
fancy.
going on. All right, so yeah, I think I got little test files down below actually.
Oh, okay. You're going
Let's
classier than
see.
paper
We're going to
cup.
calibrate. Let's do the pH first. It looks like you can choose the calibration. Wow, this guy calibrates to 6.86, 4, 9.18, 7, 4, and 10. Usually, the most important one to calibrate to is 7 or 6.86. It's cool that it can calibrate to either. I don't know why some are 7 and some are 6.86. It's annoying because you'll have,
Yeah.
you know, I have my 6.86 and my 7 solutions. Oh, awesome.
Yeah.
These are great.
Those are the best.
But so basically, from what I've learned is if you calibrate to 7, you're going to have pretty good indication of your pH. But if you want it to be more precise as you go further away from neutral, like if you're trying to monitor a pH that's normally around 5, you should calibrate to 4, or it'll start drifting out of accuracy the further it gets. So having multi-point calibration really is more accurate. But if like for this tank, for instance, I'm trying to keep my pH at about 6.5. As long as I calibrate to 7, I'm going to have a good idea of where it's sitting. Maybe it's really 6.4, but it says 6.5. That's fine by me. But if I were like, I'm trying to keep this at 4, for
You'd
whatever
calibrate
reason,
closer
I
to
would
4.
calibrate, which is super
That
acidic.
makes
You'd never
sense.
keep a fish tank. I don't know of any fish that you
Yeah.
keep that would be at acidity of 4. That's pretty acidic. All right, so let's first do pH of 7. You want to grab the pH book?
I do.
Cool.
Hi, everybody. I'm trying to do a better job of approaching the tank more slowly.
All right, good job. These guys don't get as, discus are really cool. They are the most dynamic fish. Like their personalities are so, here, you hold this, I'm gonna get the 4 ready if you can. All right,
Okay.
oh, it thinks it's calibrating to 6.6.
Do you want to use a
Let me see if we can-
6.86?
Oh, there we go, yeah.
Wow.
Nope,
No.
no, okay. This is not going as planned.
Yeah, that's all right.
Okay.
It said you have to hold it down. Maybe
Let me try
that'll.
this for a sec.
Okay. Okay. All right. Okay.
Okay.
Okay. Yeah, maybe leave it. Let it flash. Oh.
Oh, it's pissed. Let me read I'm gonna read the instructions.
Well, I think.
Okay, immerse the pH electrode into standard buffer solution. Wait, how did I get to that page? Right, we were talking about should we do this ahead of time or just do it all right in front of
We'll do it
everyone?
live.
And big regrets.
No,
But
this
here
is
it's saying,
great.
here it's weirdly
Okay.
saying,
It's going. It's calibrating to 7.
okay, because it's saying pour standard pH 6.86, which I do have prepared. Okay.
You've used these meters before too, haven't you?
I thought I had.
Yeah, and they worked
Immerse
great.
the
We're just
standard buffer
mess-
solution, then stir gently the value step. Long press the. Okay, wait. This is what it says you're supposed to do. So
Okay, yeah, let's do what the directions
you
say.
hold, I mean, the pH looks pretty What is going on?
No.
Is this meter is being weird? This could be I'm concerned about.
That it was dry. All right. Oh.
It's just going all over the place.
What's your guess that the temperature, like not that we're guessing, but like that. You know what? Let me grab the other meter. Here, you hold this.
Yeah.
Let me grab a meter that we know is lovely.
Okay.
Okay, that's right there.
You know, can you grab me the probe out of the other open unit out back in the case?
Sure.
I'm wondering if this probe seems a little whack. Let me try. So this is good, huh, guys? Let's unplug. Let me try replugging this. Okay. Oh, wait a minute. If I hold this, now press this, I think now it, nope. Okay, now it's saying that, no. It's really weird, it's drifting all over the place. I think the meter might be busted. And it's kind of weird.
I have an idea, Matt.
Yeah?
This one's also dry. For the purposes of this.
You know what, I have a working meter right over here.
Right here.
Before you do that, nope, over
Oh.
here.
Okay.
Let me grab one
Got it.
off this other tank.
The importance of keeping your pH meter in a solution. Well, let's look really quick. I want to see what our kind of 5-in-1 meter here is saying. What the pH is.
All right. I know this probe works. And this is from a different unit. This is from a Blue Lab, actually.
Oh, we got a couple going.
Might be the unit.
You might not have calibrated it right.
Huh.
Is this right? This seems low.
All right, this unit is being wild.
Well, we can just explain the concept. We don't really care about the unit. It's really just the idea of a continuous monitor and then what each parameter is in this tank.
Yeah, let's just
know.
do that. We'll go through that.
So this is, I'm using just like a handheld pH meter. It's climbing slowly. It's currently at 5.84. And it's saying the temperature is 80.9, which, as I think I mentioned earlier, you know, it's shocking how warm that these discus fish like the water. And luckily, these plants have no problem with that. And again, if the plants were struggling, it could be that they're not getting enough oxygen because the water is so warm, but these are all tropical varieties and they seem to actually love it, so that's great. And it looks like the pH just went to 6, and we try to keep it around 6.2, 6.2, so we'll see if it keeps going up. I think I might be able to, see. Let's see what the electroconductivity is, why the pH keeps going. Ooh, okay. We're at 294 parts per million. And Matt, is that lower than you would expect? That's lower than I would have expected. 294? Or is that right where you want
high.
it?
What's it? Is it a ppm?
ppm. Yeah, I'm on ppm. Sorry.
That's actually
That's a little high?
higher. I've actually been adding some aquarium salt, but that's a little high. That surprises me.
Okay. Would you like to keep them the
I like
the
them around
discus
200,
at?
but it's funny. I had it super low, and I started adding some aquarium salt in, and I think they're doing better because of it. It was almost too clean. It was at like 60 at one point, which was nuts.
Wow. This is total dissolved solids, right?
Yeah, I don't know what that is.
588. Very cool.
One sec.
And then
And
pH is 6.16. Would you add anything to that, Matt, or do you like that?
One sec. Let me
Oh,
just.
sorry, I'll let you do it. So we created this little system of what they get fed and what we try to keep their pH at. And you can see it's 6. We like it to be 6.2 to 6.6. So it's a little bit low from its optimal range. And these guys can be sensitive to having their pH off. Huh. This is Lorraine. She was very sick the last couple of weeks, but she looks much better.
Try this one more time.
All right, I know. I can feel it. You want it.
I really want this to work.
I know.
I think
It
it
will.
might be the unit though. Where did that meter go?
Okay.
Do you know where that guy? Oh, right here.
Oh, sorry, I'm in your way. Let me pop out of your way.
Cool. Cool. I'm just like perplexed.
83.1
It seemed like it was working
for
initially.
temp. It climbed up too.
What is this one saying for ppms? 442.
This
Or
one said 298.
364. all over the place.
Yeah.
That seems high too.
Can I feed them the rest of these worms while you're doing that?
Yeah, so the EC, check this out. So the EC, let's find out what the EC is, because that's like the real pure number. Let's see, EC is 0.74. So if you multiply that by 500, it would get, 370? And that should be the ppm, or is my math wrong? Or maybe they must be multiplying by, yeah, 371 right there. So see how there were 2 ppms? There's the TDS ppm, and then there was some other thing. Let's see, there was the salt ppm. I think that must be a times 700. But all these things are ultimately the same thing.
So it's saying it wants you to put all of them, all of the probes into a solution.
Yeah, but then when you read it, it says it calibrates one at a time, right?
Oh, okay.
So it's identifying that at 7, 10, it doesn't know, and then there's an error message coming out. So, I don't know. I think something's up with this meter, unfortunately. Maybe I gotta hold it even longer. It said 5 seconds, so maybe I'm not holding it long enough. That was a long time. That's right, it's 7. Do I have to press it again? I don't know. Oh well, guys, meter's not working, friends.
That's all right. We'll just use the handheld. It
Hey,
should
if your
do it.
meter's doing this, bring it back to wherever you got it. This place.
Yeah, and if it's from us, we haven't.
Yeah.
This is the only one.
I'm
we
gonna
haven't
test
sold
another
any of
one. You
these.
know, I'll bust another one out after the show. Is there anything else we want to cover tonight?
I have a question.
Yeah.
Do you want, so based on what the meter we do
Oh, yeah.
trust says, because
What was
really
the
this was just a
pH?
way to see it. So here, just talk about the things from the handheld.
Man, the second meters are just dying here.
Yeah, no, that's okay. So this is just so you can continuously monitor. You can walk by
So
and
I
see,
want my
but this
pH.
does
It's
the
funny.
same
I
thing.
used to keep my pH at like 6, and these guys in the wild live in pretty acidic environments, but I found they actually seem to be doing better right around 6.5, and seems like it's pretty sensitive, which is great for plants. So these guys pair up really well with plants from a pH perspective, but they also want super clean water, which means they pair up really well with houseplants. And even so pure, sometimes I'll see some deficiencies.
Yes.
Right, like in certain houseplant varieties. Like these guys seem to want more food than what's available in aquaponic system.
Yeah.
Or at least this type of aquaponic system. So this meter is a little older, slowly drifting up to about 6.3. So I'm fine with that. It's getting there. My guess is gonna stop at 6.3 based on what it's
Okay,
doing.
it was up to 6.2 or 6.18.
And so this is the sign of an old meter. It takes forever to get up, and it's why it's probably, now I'm just realizing why, like an old continuous meter, you don't even notice this because it's always in sync, right? It's never like just slowly
It's never
calibrating
taking
up.
its time, yeah.
You know, we do have a lot of tanks in here, so this is really frustrating sometimes if I'm like trying to do 10 fish tanks.
Yeah, a continuous
cool.
monitor that works is
And
the
based
key.
on using this one, I can see it's gonna probably go to 6.3, which is fine by me.
I was gonna say
The
something
ppm
about,
surprised
okay.
me though. I think we should do a water change. I'm curious. I want to test another meter, I think, to make sure that's accurate.
All right, we've got a comment from 07. Part of the reason that liquids tend to have higher specific heats than solids is because more energy can go into molecular motion in addition to vibrating bonds. Commander, do you wanna?
I'm not sure what this is related to.
That was in.
From way.
Okay, yeah, jump in, Jeff.
Yes.
Wait, here.
Yes, stand near.
Okay, so this is from way earlier, and honestly, I have no idea how to respond to this because I don't know the answer.
Well, I think it's a statement.
Well, it is a statement, but
Yes.
I really
Liquids
can't
tend to
explain.
have higher specifics than solids because more energy can go into molecular motion in addition to vibrating the bonds. Interesting. Okay. I think that's the key. I don't know. This sounds amazing. Well, thank you, Jeff, for saying hello. And we are trying really hard to keep up the educational content. And what the beauty of what we always are trying to do is learn from each other. And
Yes.
07 is playing in a different universe as far as the understanding of chemistry. And we are loving having you because you're educating all of us.
Yes.
I was going to say something else about EC that Matt reminded me of. So electroconductivity needs, and especially as Matt's going to double check the ppms for this, obviously we have to keep the fish healthy, so you don't want a ton of dissolved solids in the water. But when it comes to plants, different types of plants and plants in different phases of growth will need a different EC. And it's like, if you just break that down for a second, if you think about it, it's like how much food is in the water. If you just remember that's what EC is, it makes total sense. If you are running an aquaponic system over seedlings or clones, like they don't need much food. So it's like if you blast them with a high EC or a high parts per million, you're gonna burn them, you're gonna kill them. They just cannot filter out all that nitrogen. Or nitrates or whatever it might be. Whereas if you have a plant that's in flower or is producing seeds, they tend to need a lot of food, especially phosphorus and potassium, and you're probably gonna want that number to be higher. And of course, like herbs and lettuces and stuff kind of float in the middle there. So yeah, it's really cool. So you can see when Matt was pointing to this Swedish ivy, you can see there's some yellowing on the leaves here. I'm actually gonna walk this right up to the camera. I'm gonna take this little leaf off. I'm gonna take this little leaf off. A lot of them look great. A lot of them look really good, but these plants have just gotten huge. So I'm gonna walk this right up. So you can kind of see the yellowing on the leaves here. Like this kind of looks, yeah, oh, that's a good shot. It just looks really crappy. And same here. This to me, actually that might be a nutrient, another nutrient deficiency as well. But this plant is most likely trying to tell us that it needs more food in the system. And these plants have exploded. This table did not always look like this. So what we could do is either say like, okay, we're gonna keep this table going like it is. It's absolutely stunning, but we're gonna cut back the Swedish ivy, or we're gonna cut everything back a little bit, because we know we can't raise the amount of total dissolved solids that are in the tank completely, because we obviously don't want to overwhelm the fish with too much food in their water.
Hardware.
Okay, what does that mean?
This unit was busted.
It was the unit.
Something up with it.
Okay, wow,
Which is really
weird.
surprising,
Yeah,
'cause it's
really
almost-
surprising.
I don't think I've ever had a unit like that.
The joy in your voice at the discovery of the problem.
Yay, we
I
bought
can
this
feel
inventory,
it.
doesn't work. We get to-
I know, I can feel the lightness.
Now I get to reach out to a manufacturer for 2 hours.
Yeah.
Yay!
Yeah. Yay!
I mean, Matt, what would you do with that 2 hours otherwise?
Yeah.
Prove yourself?
All right, so
Learn something?
I know, yeah, right.
Look how gorgeous this is. The pothos thinks
So
it's
this
perfect.
pH actually, according to this, is so it did calibrate this, so it's perfect. Look, it's around 6.6, 6.5,
All right.
and down. So I love where this pH is. The temps
Yep.
87.8, a little warm. I don't
Okay.
know why. I turned some of these heaters down. That heater back there is overfiring. And, you know, I think I have these lights on too, and I think it might get up to this temp because I think I might have my heaters set to probably around 84, so the lights are
Oh,
off
yeah,
a
you're
long time.
adding.
But I added. And this is actually interesting. Something
Over.
no one ever talked to me about was the importance of lighting. And these fish, so I added.
Yep.
I want to show you what this tank looked like. Oh wait, is
Well,
it
and this
on? I
fish
just realized I'm not
especially.
being heard probably.
Oh, here, you want to take mine? Oh. This fish, especially Lorraine, she
Can you
was
guys hear
like
me
black.
now? Or-
Oh,
cool.
good, yeah.
Here, do you want to pull the camera towards?
Towards the tank.
Yeah. So I want to show something. Here, actually, you want to use this camera? Check this out, guys. We can probably get pretty
Zoom it
nice.
right in.
Get this a little closer.
Look at these beautiful. Can I pour? Oh, I meant to do. You said it's okay to pour these worms in, Matt. Can I put these in?
Just a little. I'll use a syringe
There we go.
for. There's a
pop.
syringe right over there.
Okay.
On the table. So check this out. So, I don't know if you want to switch to the main camera. I can show you something. Yeah. Actually, here, can we pull this all a little closer? Can I get this guy at all closer? There. Actually, is there a table? Here, you want to pass that little chair right there?
I love this. All right, while you guys are getting that set up, I'm gonna feed the fish a little bit.
Yeah.
Is this? Oh, these actually look. Are these shrimp, Matt? These are not worms.
They're brine shrimp.
Yes. Look at the
Yeah.
colors on these fish. I mean, I have never seen a more beautiful.
They're doing so much better.
freshwater
They were
fish.
struggling bad. I was
They really
feeling like
were.
a really bad discus parent.
Get come over to Lorraine. She was black 2 weeks ago, and they're cool. Will change color when they're not feeling well. And part of it was light for sure.
Yeah, so check this out. So I had just a single aquarium light, and I was worried at one point I'd been over lighting them. I was like, you know, they probably live in the shade, looking at where they live in the Amazon. I started so I cut their light, and I started doing everything else I thought right. And this was my lighting previously, and they were really dark. They weren't as energetic. They didn't look great. And so I added this other light in just for a day, just to see, you know, I don't know. I just wanted to try
even
it.
when you change
And
that,
their
she turned black.
coloration and personality exploded.
Yeah.
And I realized, like, I started wondering, you know, something to measure in water and to really be aware of is light. It's funny, a lot of growers are really worried about algae growth in their reservoirs. And I'm not always 100% sure why. I guess there's a concern that it's robbing their
Oxygen.
nutrients. What? My watch that I was talking to it. But I don't know if there's like a concern for, I can pull this one back too. Check this out. Now we can, you know, the algae, I guess there's concerns about oxygen being robbed from the root system, nutrients being robbed, but I also sometimes feel like, I think there might be some benefits, right? I think the algae, as much as it might grow, it does also break down over time. It almost like balances out some of the food. It creates biodiversity. I mean, this is a perfect world. We don't see any algae around this tank. I don't scrub this tank at all. You'll see there's bristlenose plecos. So I'm psyched. I feel like I'm getting like this general ecosystem of tropical fish, like the different
Plants,
communities, the
yeah.
plants in the aquatic system, the right lighting, and the house plants, where like this isn't a lot of work right now. And the next step for me is like to try to integrate automation of blackworms. And actually, these guys love red wigglers. So I take some of the wastewater from these guys, I put them in these flood tables over here with worms. I take the red worms and feed them back to these guys. And that seems to be really great for them. So yeah,
They love those shrimp.
they do.
Don't give them any more, right?
You can give them a little more. So the
little more.
key, here, let me show you how I,
Yeah, show me how you do
they
it.
really like to, they get kind of lost on the bottom, especially Lorraine. So this one right here, she's struggling. She's always been struggling. She's doing relatively great. I thought I was gonna lose her, and I was trying so hard. It's funny, like they're complicated because they're social animals, and she's my little buddy. As you can see, she comes right to me. And she was doing rough. You can see her tail is still recovering. She was super thin. The light made such a change in her life. I started adding lighting, and I think feeding the red worms more often has been good for her. And also, so I had split her up. I was worried she was getting bullied. And so I had a big group of discus and a small group of discus, and no one seemed to be doing right. And so I cleared this tank out of all the wood and stuff, so I made less of a chance of territoriality. And in the midst of us changing water, me and Mandy, because I thought she was gonna die. It was like my last attempt to save her. This one right here, Lorraine. Yeah,
Best fish
the
name
amount of
ever.
stress and effort I've put into that fish over the last 3 years. So we put her in here, cleared it out, and everyone just seems really happy.
Yeah.
It's like they've hit their stride, like the group is perfect, everyone's pretty happy,
plants look
everyone's
great.
getting healthy. Now it's just about maintaining that. But I'm psyched, because for a while I was really humbled by these guys.
Oh, she's so cute.
This one right here, that guy's named Zippy. He was born here. His
Yep.
mom is that blue one right there. He was the only one that made it to adulthood. His dad passed away a few years back. It was pretty surprising, actually. One day I came in and he was really healthy and died. I don't know how old he was.
Zippy's gorgeous. Look at him.
He came out beautiful.
Look at him. He's a
Handsome
stud.
fella.
Very
or a
handsome.
lady. I'm not sure. I thought it was a boy. I'm starting to think it might be a girl. Oop.
Well, with a name like Zippy, you can be anything.
You can be whoever you want.
That's right.
Yeah.
Yeah.
What's
hey,
up, Jason? How you doing, bud? Long time. Great dude. Old friend from Gardin. So yeah, the other things, I do have some other meters down here, and oops, sorry, slipped on my hand. The one I have never messed with, and after that last one, I don't know if people want to see me try, but I've owned this for like 2 years, 3 years. It's an oxygen meter. I have no idea. If JT were here, you know, next week, I'm gonna ask JT to show me how to use this bad boy. I know he knows how. I could try to turn it on. I mean, there doesn't seem to be any power. So another time. But you can measure things like this. I know the oxygen's great. Honestly, these fish would be struggling pretty bad. One thing related to oxygen that I've started thinking more and more about is duckweed. And I was always a big fan of duckweed for a long time, and I still like a small amount of it, and I use it as basically like a way to filter out fish waste, right? Like earlier
Deb.
today, about once a week, I just clean up some of the duckweed. But the thing I've started realizing about duckweed that is concerning is in tanks where I have a lot of duckweed, a real full duckweed cover, if the air pumps or water pumps turn off, I can tell the oxygen levels deplete almost immediately. And I realize there's two things that are happening. One, the root system of a plant, for most cases, is pulling oxygen out. There are exceptions, like apparently like pothos plants, which I have
right in
growing
that
into
corner.
a bunch. Yeah, and I have growing. Actually, there's roots of a pothos, or there were. Interesting. What happened? Interesting. They're not doing well anymore. There were pothos roots here.
I wonder
if the
if
discus ate them.
Oh yeah, I wonder.
But anyways, in some of the other tanks I have pothos roots like the pea puffers. Those actually put oxygen into the water, which is really great. The duckweed, I have to look into this, but my hunch is it's covering oxygen from the surface. And the thing I've heard many a time is air bubbles and air stones aren't as important as water ripples on the surface for oxygenation. And so if you think about duckweed, it's covering oxygen exposure at the surface. And also it's probably literally the roots are pulling oxygen out too.
Yeah.
So.
What hardness do you want this tank to be at?
Ooh, as low, like very, very, very low for these
Very
guys. They
soft.
want really soft water.
Do you have any buffers in here, like the seashells or the corals?
I don't. And
You just haven't needed it.
I have not needed it.
Yeah.
I have not
Do you think
needed
the biochar acts a little bit to help buffer, or is it more just making it one way or the other, more acidic, or? I think Lorraine, she's gonna come give you a kiss.
Sorry. I don't know. I think the biochar was bringing it down for a
Yeah.
bit. I think that pure water is not great. I think there's a certain level of mineralization that they want. The thing that might be, I've started feeding them more brine shrimp.
Yeah.
And I've read people a lot of times they don't like feeding discus that because they're worried about the salts.
Yeah.
I see how they're looking, and my ppms are going up
Yeah.
lately, and I feel like they are doing great. They're doing better. I can just feed them nonstop. They're super vigorous. They're getting along great.
The thing that's cool about discus when we think about feeding them is that they kind of just hang out on the sides of rivers in the Amazon waiting for food to go by. So they don't want to eat one giant meal. They kind of want to pick all day. And when we started feeding them that way versus like, it's morning time, here's a bunch of food, and then we don't feed you again. When we started giving them lots of little meals, especially of things like shrimp and worms and stuff, that really seemed to help.
They're grazers, right?
Yeah,
for
exactly.
sure.
That's a good way to say
yeah,
it.
like
Yeah.
I think they don't want bulk meals. They want, but I think in like river systems, there's probably like explosions of certain bugs once in a while.
Why do they want the water softer? Like, why do some things want soft water versus hard water?
Where they've been adapted to.
It's just a softer water. Okay.
And so I think as a result, I think like the African cichlids, Lake Malawi and whatnot are very alkaline. And so that's just what they've evolved to. That being said, there's discus that have been bred to be in hard waters, like the German discus breeding community.
Wow. That's so
Yeah,
cool.
isn't it? So, yeah, and these guys are, so I try to slow feed them like this, and it seems to do well. So, yeah, guys, any other questions, or do you guys want to call it a wrap for the evening?
Yeah, I think that's a great idea.
Yeah, guys.
This has been awesome. We got to get Jeff in here, and Lucy just joined us.
Yeah, well, from the Gardin family. Oh, sorry.
Sorry.
Sorry, Liv.
Yeah. Thank you guys so much for joining us for another Live at the Lab
Sorry.
water monitoring.
Have a great night, everyone. Until next
Have a
time.
good night, everybody. Bye.
It's the second one. It's the second live stream.